Little apology right here at the start of this one. Dimensional analysis is probably one of the least favorite things students have in chemistry. It's a little bit of math, but it's all math that you've done before. There's nothing more complicated than multiplying fractions together. If you want to get technical about it, that's about as complicated as it gets. All right. The problem is, you've probably never done a lot of word problems before, story problems. That's what a lot of dimensional analysis is. So what we're trying to do in dimensional analysis is we're trying to do math, but thinking about math in terms of real world, and thinking about it in terms of some type of united system. And the units now become part of the mathematics. There's no longer going to be the 2 plus 2 equals x, or 3y equals 12 type setups. Instead, everything we talk about, every number we talk about has a unit attached to it. So we don't talk about 3 times 5, we talk about 3 meters times 5 meters. And that changes the math, right? Because 3 times 5 is just 15. 3 meters times 5 meters is 15 meters squared, right? Because meters times meters. So you have to think about the math with the units. Okay, let's give an example. If I gave you the example of 42 grams per liter equals how many kilograms per milliliter? A lot of you would stare at that and go, I have no idea. Even though you know the relationship between grams and kilograms, and you know the relationship between liter and milliliter, by the way, if you don't, you better learn them, right? If you know those relationships, why can't you come up with the answer? Why isn't there just one simple way to do it? Well, there is one simple way, but it doesn't get done in one step. Most people are not readily going to know the conversion factor between gram, kilogram, liter, milliliter, right? That's not, 1,000 or 100. That's some number comparing the two relationships to each other. So let's get around that. Let's only deal with one conversion at a time. So if I want to convert 42 grams per liter into kilograms per milliliter, like, wait, that's the reverse of what's written. It's not the reverse, I just put them in different spots. This is kind of a notation that my old chemistry teacher taught me. Some of you've probably also learned what's called the picket fence notation. That's fine. If you know the picket fence, use the picket fence. It's essentially the exact same thing I'm doing, just drawn a little different. This is just the notation I learned. So at the very left here, kilograms per milliliter, that's the units I want. I always write that there as a reminder to that's where I've got to be at the end of my problem. Equals the next thing that I got, right? That's my known. 42 grams per liter is what I know. Now note, originally it was 42 grams over liters. Here I wrote it with the 42 specifically associated to the grams, because what that means is 42 over 1, which is the same as saying 42 grams per liter, right? So let's deal with the grams first. I know the relationship between 1 kilogram and 1 gram is 1,000. There's 1 kilogram per 1,000 grams. So I can write a relationship that says that, 1 kilogram over 1,000 grams. Essentially that equals 1. It's what we call a unit ratio. It's a ratio that compares two things to each other. So they have to be equivalent to each other. Now note the way I placed it in. I placed it so the grams are on the bottom, because those of you who remember your mathematics remember that since I have grams up here and grams down below, that those two grams can cancel each other out. Which now means if I was to solve the problem at this point, it would be kilograms per liter would be my answer. But that's not the answer I want. I want kilograms per milliliter. So I've converted the grams to kilograms. Now I need to convert the liters to milliliters. Essentially, same setup. It's 1,001 relationship. 1 liter equals 1,000 milliliters. Here, the liter on the top and the liter on the bottom cancel each other out. And that means if I do this mathematics, my answer will be in kilograms per milliliter, which is exactly what I want. Note, haven't told you to pick up a calculator yet, haven't asked you to do the math on any of these yet. Because until you've got the units right, until you can go through your dimensional analysis and have the right units at the end, there's no point in picking up the calculator because you haven't solved the problem. So if you do the math on this, it would be 42 divided by 1,000 and then divided by another 1,000. because 1 over 1,000 multiplying by 1 over 1,000 is the same as multiplying or is dividing by 1,000. So I do the mathematics and I would get 0.000042 kilograms per milliliter. That's a pain of a number to write, isn't it? I mean, it's a lot of zeros. Well, let's convert it to scientific notation. I would have to move the decimal point 5 positions to the left in order to get a 1 number. Because remember, in scientific notation, this first digit has to be between 1 and 9, right? 1 and 9. Yeah, it can only have a 1's position in scientific notation. So 4.2 times 10 to the minus 5th kilograms per milliliter. Okay, let's look at another example. In this one, we're going to convert 34.5 meters per second to kilometers per hour, or kilometers per hour, depending on who you ask. So again, I want to know kilometers per hour. I have 34.5 meters per second. I would convert meters to kilometers. 1 kilometer equals 1,000 meters. That would get me into kilometers per second. 60 seconds per minute. That gets me into kilometers per minute. 60 minutes per hour gets me to kilometers per hour. So now, to do this mathematics, multiply the things on top, divide the things on the bottom. So 34.5 divided by 1,000, multiplied by 60, multiplied by 60. You can do that all as one big thing on your calculator. They're all the same orders of operations, so it just goes left to right. Gives you 124.2 kilometers per hour, but if we look at the problem only has 3 significant figures, right? 3 significant figures in the data. So that means our answer can't have any more than 3 significant figures. Now, of course, you're like, what about these guys, the conversion factors? They have 1 sig fig. They are not data. You look at your data, not your exact numbers, which is what these are. These are definitional. There is, by definition, 1 kilometer per 1,000 meters and 60 seconds per 1 minute. So 34.5 divided by 1,000 multiplied by 60 multiplied by 60, 124.2 kilometers per hour means 124 kilometers per hour, because the 2 is 4 less, so this rounds down to 124. Okay, let's try another one, a little bit different units. If a material costs $1.45 per kilogram, how many grams would you buy at $1,000? All right. Well, now you got to realize something a lot of people miss. A dollar is a unit. When you say you have a dollar, you have a quantity, 1, and a unit, dollar. So the dollar sign can be a unit here. So let's start with $1,000. If I start with $1,000, it is 1 kilogram per $1.45. That's from the data in the problem. Dollars cancel out. You're like, wait. So like I said, dollar is a unit. Dollar can cancel dollar, right? So this would get me in how many kilograms I could buy. Convert the kilograms to grams, and I get my final answer in grams. Punch into my calculator. I get this big old long nasty number on the left. That's what your calculator says, right? It is 3 significant figures. Note, we have trailing zeros with a decimal point involved, so all of these digits are significant. These 3 digits are significant, so my final answer has 3 significant figures. So I convert this to 3 significant figures. That cuts it off right here between the 9 and the 6. So the 6 is going to cause the 9 to round up, so it's going to be 690, so 6.90. And if you count how many positions you have to move this to the left, it becomes 6.90 times 10 to the 5th grams. Okay, now again, if you're having trouble going at the speed I'm going, pause it, try to write down the answer, and try it again, okay? I also have problems that I've worked out for you that are posted. Definitely go check those out. So here's going to be our big problem. Now I'm going to say this all out, and then I'm going to pause for a second or two so you can hit pause on your browser, and then I'm going to start back up with the answer. I'm giving you those pauses in between, so if you need to pause the video to try and work it yourself, you can. All right. Apples produce cyanide gas upon chewing. It's actually the seeds that do. There is 700 milligrams of cyanide per kilogram of seeds and each seed weighs about 0.700 grams. How many seeds would it take to kill an average American male? Don't blame me, I looked this up on CDC. 88.32 kilograms is an average American male. If the lethal dose is 1.5 milligrams per kilogram, so that's milligrams of cyanide per kilogram of person. Okay? So, I'm going to take a moment to break so you guys can just sit here and hit pause if you need to think about it. The question I want you to answer is, what are the units you have in the problem? Write out the data for the problem in the units given in the problem. Okay? So let me give you a pause. Now, I'm assuming you've paused it, you've tried to write this out. Here's what you should have come up with. You have 700 milligrams of cyanide per kilogram of seeds. Wait, I just wrote milligrams over kilograms. Yeah, but that's the problem. The more detailed the units become, the more detailed you have to keep track of. Kilogram of seeds, which is one of the kilogram values up there, or it's just one of the masses up there, is not the same as kilograms of an American male, is it? No, so they can't cancel each other out. So you have to be very, very specific about the units you have. 700 milligrams of cyanide per kilogram of seeds. 0.700 grams of seeds per one seed. All right. 88.32 kilograms of male per male. And 1.50 milligrams of cyanide per kilograms of male. Okay, those are the 4 pieces of data they're given in that problem. And given those 4 pieces of data and 1 conversion factor, I can answer this problem. All right, all I have to do is put them in the right order. Look at what the question asks for. How many seeds would it take to kill an average American male? So given that hint and the units you've got, I'm going to give you another pause, see if you can write out the equation for this. All right, let's see how you did. So my unit is seeds per male. I want to know how many seeds this person has to eat. Well, if I've got seeds per male, it makes sense to have one of the units in its appropriate position from the start, right? One of the units. Because I've got male up there and I've got seeds. So if I start with either of those in the right position, I can work from there. Now, I choose to usually pick, if I've got a unit on the bottom, a unit on the bottom to put as the thing in place. It's just easier mathematically to keep that one stable and try to change the top one. So let's say, okay, we'll take that, male on the bottom. That means that my first unit is 88.32 kilograms of male per male. All right, so that eliminates one of my factors up there. Now, next thing is to try to step that top unit to the top unit I have in the answer. So I'm starting at kilograms of male per male, and I'm trying to get to seeds per male. So my first step, since male is already where it needs to be, is to try to convert kilogram into male into something else. So I look for another piece of data up here that has kilogram of male. And this last part right here, 1.5 milligrams of cyanide per kilograms of male. All right, there they are. Plop it down there, kilograms of male cancels each other out. Next, I try to convert milligrams of cyanide to something else. Well, this last part here, I got milligrams of cyanide. All right. So now here, I have to flip it upside down. All right. So if I try to use this unit up here down in the problem, I'm going to end up with milligrams of cyanide or kilograms of seeds. So if I try to solve the problem, what I'm going to end up with is milligrams of cyanide squared per kilograms of seed times male. That doesn't mathematically work. I want to flip this upside down, which is valid. I can flip it upside down. It's still a 1-to-1 ratio here between these two. These still equal each other. Kilogram of seeds per 700 milligrams of cyanide. Milligrams of cyanide cancels. Next up, try to convert kilograms of seeds into something else. Well, there's a problem. I've got kilograms of seeds and I've got grams of seeds. So I need to have a conversion factor in here to convert my kilograms of seeds into grams of seeds. And you're like, do we know that holds true? Kilograms per grams? Yeah, of course it does, right? A gram is a gram is a gram. It's like the old riddle goes. What weighs more? A ton of feathers or a ton of bricks? And you're like, oh, well, the ton of bricks, but they're both a ton, right? So 1,000 grams of seeds equals 1 kilogram of seeds, just like 1,000, pounds of bird doo-doo equals a kilogram of bird doo-doo, right? Works out the same either way. So kilograms of seed cancels. That's going to leave me in grams of seeds per milligrams of cyanide. One more conversion factor. Use the last of my units up here, the 0.7 grams of seeds per seed. That eliminates grams of seeds, leaves me in seeds per male, and I get that number out of my calculator, but it goes to 3 significant figures, right? 3 significant figures for the 0.700 and the 1.50. So that means 270 seeds per average American male to kill them with apple seeds. So I hope this helped a little bit to explain dimensional analysis. Be sure and start the practice problems that I've given you.